Let's do another example. This example illustrates a battery charging another battery. So notice that we have two batteries in this circuit and two resistors. We have a 6-volt battery and we have a 9-volt battery. That 9-volt battery having a higher potential difference across its terminals will, in a sense, overpower the 6-volt battery, driving current through it from high potential to low potential. For this problem, let's just go ahead and analyze this circuit, and we're going to find the current in and the potential difference across each resistor. Let's begin with our own sketch of this scenario. We have a 6-volt battery, which I'll represent as Psi, and Psi, the EMF of that 6-volt battery is 6 volts. And we'll just go ahead and call that the EMF 1. That 6-volt battery is attached to a 4-ohm resistor, and that 4-ohm resistor is attached to the 9-volt battery, which we will label as EMF 2, which is at 9.0 volts. And notice 9.0 volts is equal to 3/2 of 6 volts, or in other words, 3/2 of the EMF of battery 1. The negative terminal of battery 2 is attached to a 2-ohm resistor. We will call the 2-ohm resistor R1. R1 has a value of 2.0 ohms, and we'll call the 4-ohm resistor R2, where R2 has a value of 4.0 ohms, which happens to be twice the resistance of resistor 1. Our goal is to find the current across each resistor. Since this is just a single loop, the current everywhere in this single loop will be constant. So if we find the current anywhere, we will have found the current everywhere. Now, we're going to use Kirchhoff's laws to help us analyze this circuit. And before we do that, it's useful to illustrate nodes between different components of our circuit. I'm going to start with labeling node A to be at the negative terminal of battery 2, since battery 2 is at a higher potential than any other component in the circuit. We will say node B is at the positive terminal of battery 2. We'll say node C is in between the positive terminal of battery 1 and resistor 2. And we'll say node D is between the negative terminal of battery 1 and resistor 1. Let's choose our path of analysis going from the highest known potential to low potential. So the battery 2 at 9 volt is our high source of potential. So I am going to analyze our loop from high potential to low potential. So in other words, in the counterclockwise direction. Now, since this is a single loop, and since that 9-volt battery is at a higher potential than anything else, I believe it's a safe assumption to say that the current will also go in the direction from what we perceive to be high potential to low potential. It's important to indicate our path of analysis and our current direction, because how we analyze the voltage across the resistors and how we analyze the voltage across the batteries will depend on our assumptions and our choices at this point. What we are going to use is we're going to use Kirchhoff's law for voltage loops, which says when we go in a complete loop, and we're going to start from A and end up at A, When we go in a complete loop, that must sum to be equal to 0 volts. So this means that when we start from point A, the voltage from A to B, plus the voltage from B to C, plus the voltage from C to D, plus the voltage from D back to A, must sum to 0. Well, let's look at each of our components in turn, beginning with battery 2. So battery 2 has a potential difference from A to B. Well, let's look at this. So battery 2, we have chosen our analysis direction to go from the low potential terminal to the high potential terminal. Since we are going from low to high potential across our battery, we are going to say that the potential difference from A to B is equal to a positive EMF of battery 2. That positive is because we're analyzing the voltage from the negative terminal of the battery through to the positive terminal of the battery. Now let's look at the segment from B to C across resistor 2. So the potential difference from B to C across resistor 2, let's illustrate this resistor. Here is B, here is C. We are analyzing from B to C, and we are assuming our current will flow from B to C. Since our voltage analysis is in the same direction as current, we could say that the potential from B to C is equal to A minus the product of the current and the resistance of resistor 2. The minus sign occurs because whenever we analyze potential difference across a resistor, if we analyze it in the direction of current, that means we're going from a high potential side to a low potential side based off of our assumption. And being consistent with our assumption, if we go from high to lower potential, that means the potential difference across that resistor is a potential drop. It changes in the negative direction. Now let's look at the potential from C to D. This is across battery 1. Now, in going from C to D, notice we are going from the positive terminal of battery 1 to the negative terminal of battery 1 as we go in our circuit. So here is the direction we're analyzing. And that analysis direction going from the positive terminal to the negative terminal means that the potential difference from C to D across battery 1 is a negative change. So in other words, when you go from a positive terminal of a battery to a negative terminal of that battery, then that battery will lower the potential by the amount of its terminal. So in this case, our potential is lowered by negative the EMF of battery 1. And finally, the potential difference from D back to A is the potential difference of going across resistor 1. So here's point D, here's point A. We are analyzing from D to A, and our current goes from D to A. Since our current is in the same direction as our analysis, that means the potential from D to point A reduces, and it reduces by an amount given to us by Ohm's law. So the potential difference across resistor 1 is equal to minus the current in our circuit times the value of the resistance for resistor 1. So now we have all the pieces we need to find the current in our circuit. Remember, Kirchhoff's loop law for voltage says the potential difference starting at point A and ending back up at point A is equal to the potential difference from A to B plus the potential difference from B to C plus the potential difference from C to D plus the potential difference from D back to A, and that must all sum to be 0. We have indicated the potential difference from A to B is equal to the EMF of the second battery. The potential difference from B to C is equal to minus the product of the current and the value of the resistance for resistor 2. The potential difference from C to D is equal to minus the EMF of battery 1. And the potential difference from D back to A is equal to minus the product of the current in this loop times the resistance of resistor 1. That all must sum to be equal to 0. So we are trying to find the current in our circuit. So I see with a couple of algebraic steps, I could factor out the current from resistors 1 and 2 and set that equal to the difference in potential between the two batteries. This means that the current is equal to the difference in potential between the two batteries divided by the total resistance of our circuit. So we have the current equal to the ratio of the difference in potentials of the batteries over the total resistance of the circuit. So the EMF of battery 2 is 9.0 volts. The EMF of battery 1 is 6.0 volts. The value of resistance for resistor 1 is 2.0 ohms. And the resistance of resistor 2 is 4.0 ohms. This means we have a net of 3 volts in the numerator and 6 ohms in the denominator. This means that the current in our circuit is equal to 0.50 volts per ohm. And remember, a volt per ohm is the same thing as an amp, the unit of current. Now that we found the current in the circuit, we could use this to find the potential difference across each of our resistors. So let's look at how we label things. So we need to find the potential difference across resistor 1, which is the potential difference from D to A, and the potential difference across resistor 2, which is the potential difference from B to C. So earlier, we said that the potential difference from B to C, this is across resistor 2, is equal to minus the current times the value of resistance for resistor 2. Now, I normally don't like to reuse intermediate results, but since the current we found was exactly 0.5 without any rounding, I'm going to go ahead and use that value of the current without going back and plugging in the variables. So this would be 0.50 amps times the value of resistance for resistor 2, which is 4.0 ohms. And this ends up being equal to minus 2.0 amp ohms. Okay, so what is an amp ohm? Well, remember an amp is a volt per ohm. So an amp ohm is a volt per ohm times an ohms, which is a volt. So that means the units of the potential across resistor 2 is equal to the volt, which is exactly what we are looking for. So the value of the potential difference across resistor 2 is equal to minus 2.0 volts. Now we got to find the potential difference across resistor 1. This is pretty straightforward as well. It's the current going across resistor 1 times the value of resistance for resistor 1, and that was a potential drop, so I have a minus sign in front. This then is equal to minus 0.50 amps times 2.0 ohms, and this ends up being equal to minus 1.0 volts after we do our unit check. So the potential difference across resistor 2, we can say is half the potential difference across resistor 1. Or I said that backwards. The potential difference across resistor 1 is half the potential difference across resistor 2. And that makes sense because it's just a single loop. Both resistors have the same current. So the resistor that has the lower resistance will only have half the potential drop, in this case, as the resistor that has the higher resistance. If resistor 2 had 3 times the resistance of resistor 1, then the potential drop across resistor 1 would only be 1/3 of that of resistor 2, and so on. So now we found our currents and our potential drops for our resistors.